Call you right now.
All right.
Okay.
So much better. All right. Did you say you were sending me something?
No, I think I can verbalize everything.
Okay.
So the first one is a trig identities problem.
Okay.
It's sine over cosine plus 1.
Like that?
Yeah. Plus cosine minus 1 over sine. All equals 0.
Okay. Just trying to, I know how to do it. I'm just trying to think if it makes more sense if I take it over to the other side. I think it does. In other words, this is a verifying problem, right? Now notice when I take it over the other side, it makes it minus, but as all I have to do is switch the numerator into 1 minus cosine. That's correct.
Okay.
Okay? In other words, I took this second term to the right side with a negative sign in front of it, and then I switched the numerator to account for that negative sign. In other words, a minus b is always equal to minus b minus a. You can always do that. You have two things. If you want to make it negative, just switch it.
Okay.
If they're being subtracted. Now, this is actually one of the more common trig identities to verify. What you want to take notice of here is this cosine plus 1. That is what you're looking for to multiply by the conjugate. In other words, I'm going to multiply that thing by cosine minus 1 over cosine minus 1. The reason being is that it turns the denominator into cosine squared minus 1, which is a trig identity for sine squared. You with me?
Yeah.
Whenever you see this kind of thing, cosine plus 1 or even cosine minus 1 or 1 minus cosine, the first thing you should think of is I want to multiply it by its conjugate.
Right.
What that gives me is, and I don't multiply out the top because you'll see why, what I've got in the bottom is cosine squared minus 1, which becomes sine squared. Now that sine cancels with that exponent, and I'm left with cosine minus 1 over sine, which is what I started with. No, it isn't. That's what I started with. Did I write it correctly? Were these all in parentheses like this?
Yes.
So, let's try a different tactic here. I think I just made a math error, but I'm not sure. Let's take that over to the other side, only this time let's just put a minus in front of it. That's correct, isn't it? Now, when I multiply the left side by the conjugate, I get sine times cosine minus 1 all over cosine squared minus 1. Cosine squared minus 1, that's equal to minus sine squared. That's where I made my mistake. Cosine squared minus 1 is not sine squared. Sine squared plus cosine squared equals 1, so cosine squared minus 1 must be minus sine. And that means I can cross that out, put a minus sine squared. Now I can cross that out, and now I do have that. I've got cosine minus 1 over minus sine, which is exactly what that is. I can put that minus sign either in the numerator or the denominator or out front, does not matter. Okay? The key was this cosine squared minus 1. I'm so used to substituting the trig identity sine squared for that I didn't think for a moment that it's minus sine squared.
Right.
That's why I didn't get my sign right the first time I did it.
Okay.
And I was thinking I made my mistake on the right side of the equation when I made it on the left. Two negatives make a right. Two wrongs do make a right. All right, what else you got?
So the next ones are graphing.
Okay.
And it says identify the amplitude, phase shift, period, and vertical shift.
Okay. Are they so they must be giving you the graph?
No, they're giving the equation.
Okay, go ahead.
So it's y equals sine of 1/2 x minus pi plus
With the 1/2 outside or inside the parentheses?
inside the parentheses.
It matters greatly. 1/2 x what?
Minus pi plus 2.
Now, the reason it matters is it doesn't change b. b is still 1/2. So it doesn't change the period. What it does do is changes the phase shift. That is not, pi is not the phase shift. If I want this thing to be the phase shift, then I got to get this 1/2 outside the parentheses in front. Then I can call that the phase shift. And basically what the phase shift is going to be is this c divided by 1/2. In other words, if I factor out that 1/2, is that not what I get?
Yeah, it is.
Exactly. So, A is what?
1.
B is what?
1/2.
Period is what?
2 pi.
Period is always 2 pi over B.
Right.
That makes it 4 pi.
So 4 pi.
Correct.
Okay.
Remember that this is very much like a horizontal stretch factor, right?
Right.
It's exactly that. I don't know why they insist upon calling it something different, but it's a horizontal stretch factor because it's less than 1, which means my period gets stretched out horizontally when that thing is less than 1. If it's greater than 1, it gets scrunched up. What's the phase shift?
Right 2 pi.
And what is the vertical shift?
Plus 2.
Up to.
Right.
Up to or down. One or the other. And then they want you to graph it?
Yes.
Try to graph it in that small area. Where am I going to start? I like starting at the, well, when there's a vertical shift, I like starting there. In other words, let's redraw the line of symmetry. The normal line of symmetry, if you don't have a vertical shift, the line of symmetry is the x-axis, right?
Right.
But if there's a vertical shift, it moves that whole line of symmetry up. Let's see if I can draw it. Oh, holy smokes. Grief. I had too many sessions today. See if I can draw a horizontal line and now a vertical line. Okay, gosh, that's going to have to be, yeah. That's embarrassing. What I want to do is move the horizontal line of symmetry, which I'm going to represent. See, dotted lines are easier to do. I'm going to represent the horizontal line of symmetry with this dotted line. It's going to go to 2. Where's my maximum and my minimum?
At 3 and 1.
Where is my first starting point?
2, 0.
2 pi, 0. Actually, let's start over again. My first starting point I'm going to label on the x-axis, okay? It's 2 pi. There's a phase shift of 2 pi to the right, correct? So
right.
I'm going to start on the x-axis there. Where am I going to end? I realize these points are going to move up because of this vertical shift, but there's a method here that you want to follow, I think, every single time. And that method is find out, based on the phase shift, where your starting point's going to be and where your ending point's going to be. What's my period?
4 pi.
Where's my ending point?
6 pi.
So that's all I got to do. Now the key thing is to quarter this thing up. You need 4 quarter points between your beginning point and your ending point. What's the middle one?
4 pi.
What's this one?
3 pi. And 5 pi.
Okay, those quarter points. Now here's what I know about the sign. I've accounted now for everything in the function. I've accounted for the 1/2, the minus 2 pi, and the 2. So I know my sign starts on the line of symmetry, right? And goes up. So the next quarter point is where it hits its maximum, comes back down through the next quarter point, goes through the line of symmetry again. At the next quarter point, goes down and hits its minimum. And finally, at the last quarter point, comes back up to the horizontal line of symmetry. Now I just connect that with a nice sine-looking curve, and there you have it. And to me, that exact pattern is the best way to go.
Okay.
Particularly the part where you start at 2 pi, figure out that the period is 4 pi, meaning you're ending at 6 pi, and then quarter that up. In other words, this process right here is by far the most important part of that process.
Okay.
Sometimes these aren't so easy to quarter up. Okay?
Right.
This particular one was easy to quarter up. But let me just give you one that wouldn't be so easy to quarter up. Let's say we're going from pi over 4 is our phase shift. And this time we'll make a period of 2 pi. Now let's make a period of 3 pi. So this has got to be 13 pi over 4, right? If I add 3 pi to pi over 4, that's 12 pi over 4, so that's 13 pi over 4. Now, how do you get that point? In other words, how do you quarter this up? Add the two numbers, divide by 2. That's what you always want to do. So what is it?
7 pi over 4.
Correct. To get this quarter point, add the two numbers, divide by 2.
4 pi over 4.
And I like writing it like that. Better than pi. You see why?
You can tell where it is.
You can tell exactly that you're correct. In other words, sometimes you don't always want to simplify these things. If I write it like this, I know I got it right. It's 3 pi, and the numerator difference here, 3 pi, 3 pi, 3 pi. So I know that I've quartered it up correctly. But truly the secret to quartering it up is just to take your two endpoints, add them together, divide by 2, that's the midpoint.
Okay.
Okay? What else you got?
So the next one is says to plot and label the following points and convert to rectangular form.
Okay?
Negative 2, comma, 4 pi over 3.
Polar is, that's R, that's theta. In order to convert to rectangular, there's two primary conversion factors. Have to memorize. No getting around it. What are they? What's x equal to?
R times cosine of theta.
And y?
R times sine of theta.
Well, there you have it. This one's easy. What's x going to be equal to? Minus 2 is r. What's the cosine of 4 pi over 3?
Negative root 3 over 2.
I think it's negative 1/2.
Oh, yeah.
So it's 2 times negative 1/2. So the x-coordinate is 1. What's the y-coordinate? Y-coordinate is minus 2 times sine of 4 pi over 3. What's the sine of 4 pi over 3?
Negative root 3 over 2.
So the y-coordinate is root 3. Now, let's see if that makes sense. That's how you do it, and we only had to know these two conversion factors. When you're going the other way, you need another one. You need to be able to figure out theta. It's a little harder to go the other way. But we can check to make sure that we at least are in the right quadrant. So if I wanted to plot that, I would go 4 pi over 3, and then I would go minus 2 in the other direction, correct?
Right.
So that point with that distance is my polar coordinate minus 2.
Oh.
Sorry?
No, that makes sense. The hypotenuse is 2, and then the opposite side is root 3.
Right. Now,
Adjacent is 1.
and that's in the right quadrant, correct? In other words, the x and y coordinate of that look like they very easily, whoops, hold on, let me redraw it. I know that's a 60-degree angle. Well, if that's a 60-degree angle, that's root 3, and that's 1. So the x-coordinate is definitely 1. The y-coordinate is definitely root 3.
Right.
Yeah, just for the heck of it, let's take this same problem and figure out how to take the rectangular and put them into polar. Because then I can demonstrate that. I'm sure you have other problems that are like that also, but let's just use this one since we're talking about it. First of all, r is r squared equals x squared plus y squared. There's that conversion. which makes r the square root of 1 plus 3. Excuse me, r is plus or minus the square root of x squared plus y squared.
Right.
So r is plus or minus 2. Interesting. Huh. Very interesting. I never realized that that is problematic. Let's not start with r. Let's start with theta. This is the fun one. Theta is defined as the inverse tan of y over x, which makes a lot of sense, but only if x is greater than 0. Otherwise, theta is the inverse tan of y over x plus pi if x is less than 0.
Right.
So, for us to figure out theta, let's take the inverse tan of root 3 over 1, not going to add pi, what the heck? First of all, a point in the x and y plane can have lots of different polar coordinates.
Right.
It's not a unique solution. So when you're going from xy coordinates to polar coordinates, I'm not necessarily going to get back to minus 2, 4 pi over 3. And in fact, I'm going to get theta is pi over 3. And I'm going to get r is positive 2.
Right.
And that is polar coordinates that plot the same exact point as minus 2, comma, 4 pi over 3.
Right.
So this really is the answer, and the way we got it was doing it how I was thrown for a loop because of r, but r is the positive square root also. So r is definitely 2, but it could be negative 2 because it's plus or minus when you take the square root of both sides when you solve an equation. So I could have a negative 2r, but then if I have a negative 2r, I've got to make theta 4 pi over 3. So
Right.
probably would work better if you give me the problem to go backwards. Do you have one? Yeah, there are going to be multiple answers. That's why that problem was confusing. I probably shouldn't have chosen that one.
Right.
Because when I went backwards, I didn't get the same answer as we started with. But that's okay. That's very okay. Polar, you have multiple answers. So, what else you got?
So this next one is in, we have to convert to polar complex form.
Okay. A complex number that's in the form a plus bi.
Yeah.
So what's the complex number?
Negative 2 plus 2i.
All right, here's the formula. It's equal to r times the cosine of theta plus I sine of theta. That's the polar form. What is r? R is the square root of a squared plus b squared. So what is r in this case?
2 root 2.
Okay. And we need theta. Again, the definition for theta is exactly the same. Theta is the inverse tan, only instead of y over x, it's b over a if a is greater than 0, and it's the inverse tan of b over a plus pi if a is less than 0. And notice that there's very few places in math where you care about just the denominator. Usually you care about b over a, whether that's positive or negative. It's rare that it's just the denominator that we care about. Well, what is the inverse tan of 2 over minus 2? Or, excuse me, plus pi, because the denominator is negative. What's the inverse tan of minus 1?
3 pi over 4.
Actually, if you put that in your calculator, that's not what it'll give you.
Right.
It'll give you minus 45 degrees, right?
Right. Yeah.
Okay, so minus pi over 4 plus pi is 3 pi over 4. So theta is 3 pi over 4, but I had to add pi to get there.
Right.
That's why you add pi, is so you get in the right quadrant. Okay, now let's see if we're close. There's two ways to do this. And incidentally, this is not going to satisfy you much, but here's what the proper answer is. 2 root 2 cosine of 3 pi over 4 I sine of 3 pi over 4. That's my final answer right there. There's no simplification going to be done. Guess what would happen if I simplified it?
You get to the original form.
Exactly. In other words, if I plug in what cosine of 3 pi over 4 is and sine of 3 pi over 4, I end up back there. So I wouldn't accomplish much. So when they say put it into the polar trig format, they want it to be cosine of an angle, not the result of that, just the cosine of that angle.
Okay.
Now let's graph it on the imaginary plane and see if we're in the right quadrant. Well, when you graph an imaginary number, the horizontal is the real, the vertical is the imaginary. Well, the real is minus 2, b is plus 2, so I'm right there, and that angle is 3 pi over 4.
Okay.
It puts me in the second quadrant. And if I really wanted, in other words, if my life depended on it, and I wanted to make sure that I have it right, I'm always reducing this thing. In other words, like I said, if I was going to live or die based on whether that's the correct answer, I'm figuring out what this is and make sure that this is equal to minus 2 plus 2i. And it will be. And that will be what proves that this is correct. Follow me?
Yeah.
Okay. William, I am stacked up solid tonight, so
Not a problem.
I gotta go, but I will
thank you.
talk to you next time. Yeah. When is your final?
My final's next Thursday, I think.
Okay. So I'll have more.
Sorry. It's well, I already had my final actually, which is weird, but I have a quiz on next Wednesday.
Oh,
so.
okay. Oh, and you have another appointment scheduled here, I see, on Thursday also.
Yeah, I've got Thursday and then next Tuesday before the quiz.
Okay,
so.
cool. Talk to you next time.
Yeah, bye, Mr. Count. Thank you.
Bye-bye.